This is the third and last lecture of chapter 16, which deals with substitution reactions at acyl carbons. Remember, the acyl here means a carbon oxygen double bond. So in this lecture, we'll cover the following: substitution reactions at acyl carbons involving amides. Next, the reaction involving carboxylic acids. Next, we'll look at some unique reactions involving tanyl chloride, I'll give you the structure, and oxalyl chloride, I'll give you the structure. But you'll see it's basically a substitution reaction at a carbon oxygen or sulfur oxygen double bond. And lastly, we'll look at applications of substitution reactions to our favorite, synthesis. So let's begin. First, we'll look at amides. So here is an amide here, as you can imagine, because of the NH2 that's bonded to the carbonyl group here, or the acyl group. For a substitution reaction, we have a nucleophile here with its electrons. Remember, a nucleophile here is essentially a Lewis base. It must have at least one unshared pair of electrons. Those electrons bond to this carbon because it's partially positive, because this bond here is a polar covalent bond. These electrons swing up, as you can see here, and this is a tetrahedral intermediate, as you will recall. And of course, these electrons swing back in because the carbon oxygen double bond is a favorable bond, so it swings in, and the NH2 leaves with its electrons. Notice the bonding electrons are here. So if it leaves with its bonding electrons, we have NH2 bonding electrons, and of course an additional pair of electrons that were there before. So this is the amide anion. By the way, that's incorrectly spelled. That's the amide anion. It's an extremely poor leaving group. Why? Because the pKa of its conjugate acid is 37. Very weak acid. If it's a weak acid, it means that this is a strong base. And we have defined earlier that a leaving group, a good leaving group, is a weak base. In other words, a species that can accommodate the negative charge. So this is an extremely poor leaving group. So this reaction here is not a feasible reaction as written. However, if we should carry out the same reaction in an acidic medium, in other words, here we're using an acid as a catalyst. So as you can see here, the same amide. In this case, these electrons from the oxygen, the more basic site, bonds to the proton. Of course, remember, a proton here is a hydrogen without its electrons. So it forms a bond right here. And of course, if it does that, oxygen acquires a formal charge of +1. As you can see here, these are resonance structures. But the bottom line is that this carbon is now electrophilic or positive. So if it's positive, as shown here again, the nucleophile with its unshared pair of electrons can bond to form a tetrahedral intermediate. That is not the product, that's an intermediate. In the next step, here's the intermediate again, has an pair of electrons here, we still have acid around because that's the catalyst. It can bond to the acid, and we have here a protonated amine. This now becomes the leaving group. As you can see here, leaves as ammonia. The question now is ammonia a good leaving group? Let's find out. The conjugate acid of ammonia has a pKa of 9.4. Now that's a good difference between the conjugate acid of the NH2 that leaves. So this is a fairly weak, a fairly strong acid, not the strongest, but stronger than your typical acid. So it means that its conjugate base here is weak. So this is a weak conjugate base, which means that it's a good leaving group. So this reaction here, in the presence of an acid, produces a better leaving group than the NH2 in the absence of your acid. This is what's generated, and of course the proton is regenerated to give you your product. So once again, this H plus is a catalyst. It is used but not consumed in the reaction. So that's by definition a catalyst. So an amide can undergo reaction, a substitution reaction, but it can do it in the presence of an acid, H plus, as a catalyst. So let us look at some examples here. Here's an amide, and here is the nucleophile water. So this is water here. As you can see here, that's the nucleophile. So this reaction is generally described as hydrolysis of the amide. Notice an acid is present, and because the reaction is so reluctant, we have to heat it. So heat is also present. So the substitution is the OH from water substitutes for the NH2 to get a carboxylic acid. And of course NH4. You may be wondering why NH4 plus instead of NH3, and that is because NH3 is a base, and in the presence of an acid it will protonate to give the ammonium ion. Here's another example. Benzamide, an amide, presence of a nucleophile. Nucleophile here is water, presence of an acid as a catalyst, and heat to make sure the reaction goes. Substitution occurs in which the NH2 is now substituted for the OH from water, and we have here our carboxylic acid, benzoic acid, and of course our leaving group is now the amine, but it's protonated because of the presence of an acid to give us the ammonium ion. Let us look at another example here, and this is the reaction with metalhydride on the amide. Remember, the metalhydride really has H electrons negative. That's the hydride anion. That's the hydride anion. Notice it's a very strong Lewis base because of the bond-shaded pair of electrons on hydrogen. It wants to give it up, so it's very reactive, strong reducing agent. So it comes in here, as you can imagine, and it would like to kick this out, but the product that's actually isolated is the amine, primary amine, so it remains. So as you will see in the text, the hydride comes in here, these electrons swing out, eventually this O leaves and combines with the aluminum to form a compound. So again, very tricky, because this one is unique, because the NH2 doesn't leave, it's the oxygen that leaves, and here we have the product here, which is of course two hydrogens here coming from the hydride, lithium aluminum hydride, to form that as a product. Bottom line is you can take an amide and react it with lithium aluminum hydride followed by hydrolysis to get a primary amine. Same here. So remember that this is the one that will eventually leave, and the mechanism is in your book to get here a primary amine. Okay, let us look at another type molecule, the carboxylic acid. So this is your carboxylic acid. Here's an OH. So the question now is, can this undergo a nucleophilic substitution reaction at the acyl carbon as we've seen before? So let's see. Here are the electrons from the nucleophile. It can come in and form a bond right here. And of course these electrons will go up. These electrons will come back in to form a carbon-oxygen double bond, and this will leave with its electrons. You'll recognize that to be the hydroxide anion. So, in order to determine if this is a feasible reaction or not, we can decide if this OH is a good leaving group. It is not a very good leaving group because it is a strong base. How do we know that? Because the conjugate acid, which is H2O, has a pKa of 15.7. As you can see, that's a fairly weak acid. And a weak acid gives a strong base. Let me write that. Weak acid gives a strong base. Or the conjugate base of a weak acid is strong. So if it's a strong base, it is a poor leaving group. So this reaction here is not a favorable reaction as written. It's not a favorable reaction as written because the leaving group here is a poor leaving group, strong base. You can imagine what will happen here. In the presence of an acid, in an acidic medium, using an acid as a catalyst, we can get this reaction to go. So the first step is the protonation of the oxygen. Notice again the arrow movement. We're moving these electrons here to bond to the proton, which has no electrons, to form this bond right here. And of course the oxygen, since it has 1, 2, and 3 bonds to it, has a formal positive charge. Don't forget your formal charges. What it reveals also is that this carbon here is positive after drawing different resonance structures. So the nucleophile can attack this carbon, since it's electrophilic, to give this tetrahedral intermediate. Notice because this is protonated, we can take it back off to get a tetrahedral intermediate as shown here. That's not the product, it's a tetrahedral intermediate. As shown on the next slide, it would prefer to form a carbon-oxygen double bond. But if it came back in, this is a poor leaving group. So what happens is these electrons here can react with the H plus to get here a protonated OH. This is now a good leaving group because it leaves as water. How do we know it's a good leaving group? Because the conjugate acid of this has a pKa of minus 1.7. Notice this is the conjugate acid H3O plus, and this is the conjugate base H2O. So it's the acid-base conjugate pair relationship, strong acid, weak conjugate base. So this is a weak conjugate base, making it a good leaving group. So this reaction here is favorable, at least compared to the reaction without an acid. This is an intermediate that's protonated, so you can see you can lose your proton here or regenerate your catalyst to give your product with a new CNU bond. Substitution reaction at an acyl carbon. Let's look at some reactions now. So, here's one, esterification. In other words, we're reacting a carboxylic acid with an alcohol. As you can imagine, it's nucleophilic because here are the electrons. And the reaction is reluctant, but in the presence of a catalyst, H+, it will go. Sometimes you have to heat it, but it's much easier than the amide. So this reaction here is a substitution of OH for the OR group, as we've seen here. So here's our ester right here. This is ethyl benzoate. As you can see here, these compounds, these esters are very important compounds in the flavoring and cosmetic industry. So this is used as fragrance and preservative. Here's another one, acetic acid and isoamyl alcohol. So here's the alcohol. Here is the acid. Here's the potential leaving group. Here is the catalyst. And the reaction will go to give isoamyl acetate. And of course, this is the odor of banana. I think you'll make this in the lab. And whenever you guys make it in the lab, the entire floor have the fragrance of bananas. Let us look at another type of reaction. Here, it's still acid, so it's a benzoic acid. But here, the nucleophile is an amine. So as you can imagine, this will leave and this will bond here to give you an amide. So that's a secondary amide depending on the groups bonded to nitrogen. If it's ammonia, of course it's a primary amide. If it's a primary amine, you get a secondary amide. And if it's a secondary amine, you get here, of course, a tertiary amide. So again, look out for these reactions. They are typically acid catalyzed. And of course, just to point out something here that you learned in Gen Chem, it's an equilibrium reaction, as you can see here. So you can drive the reaction to the right or to the left based on shifting the equilibrium. So here, what's done in industry is if you can take off the water once it's formed, you drive the equilibrium to the right. That's called Le Chatelier's principle. If a stress is brought upon a system, it shifts to accommodate that stress. So the stress here is the removal of one of the product by dehydration or distillation. The equilibrium shifts to the right, so you get a lot of your amide. Same process can be done for the esters. Here's the reaction with a metal hydride. So here we have lithium aluminum hydride, which essentially provides H-. That's a hydride anion. As you can imagine, it's going to react here. And if it reacts here and these come out, we have two groups here that have a carbon that have two oxygens bonded to it. As you'll see in the book, this is a very strong base, so it's going to take off this hydrogen first. So it has two oxygens. So one leaves, and of course the other one, another hydride comes in, so you end up with a primary alcohol. So these two H's here are coming from the lithium aluminum hydride, the reducing agent, to form your primary alcohol. Here's another example. Carboxylic acid, right here. Lithium aluminum hydride supplies H-. H- bonds here. One of the H's, Oxygen leaves, and of course in a workup step adding water, we have this as our product. So again, we'll do synthesis in a minute. Carboxylic acids are compounds that are relatively easy to make by oxidation, as you will recall from previous chapters. But we can carry out a reduction to make an alcohol, as shown here, using lithium aluminum hydride. Let us turn our attention now to another type compound. First one we'll look at is oxalyl chloride. Very unique and very reactive molecule. Let's analyze it before we look at the potential reaction. Here's a carbon, carbonyl, bonded to a very good leaving group, electronegative also, and this carbon is bonded to an oxygen, which is also electronegative, so this is very, very positive. Same here. This carbon is bonded to a chlorine, very electronegative, oxygen, very electronegative, so this carbon again is very positive. So as you can imagine, this is a very, very reactive molecule. Whenever we work with it in the lab, we'll have to work in the hood because just moisture from our skin gets on that molecule, it reacts. So it's an irritant for the skin. So we have to use gloves and use the hood. As you can imagine, here's the nucleophile. And these electrons can attack here. We have some good leaving groups here. And eventually, what happens is that this OH here is substituted for a Cl from this molecule. We'll see the mechanism on later on. No, I think the mechanism is in the book. The one we'll discuss is this one for the mechanism. So here's another molecule, pretty similar. It's called tanyl chloride. Does the same thing. Let's look at this. This is a sulfur in this case, bonded to a chlorine and another chlorine, very electronegative, and to an oxygen, very electronegative. So this sulfur here is very positive, very electrophilic. So as you can imagine, this oxygen here can bond to this sulfur, kicking out a chlorine, and we'll see on the next slide that eventually we get the chloride. So what we're doing here is we're converting a very poor leaving group to a good leaving group. A poor leaving group to a good leaving group. You'll see the importance of that in a second, because whenever you have a reaction to carry out, you need good leaving groups to make these reactions go. So let's look at the mechanism. And it's in the book in more detail, but it's just condensed here. So here is tanyl chloride. So these electrons here attack this carbon, as you can imagine, not surprising because it's electrophilic. These electrons go up because you need to have 4 bonds to sulfur here. And of course here we have the intermediate here. This comes in and the chloride goes because it's a good leaving group to form this. Chloride being a base can abstract this hydrogen to get this intermediate. This intermediate is not stable. Let's see why. It's not stable because this portion here can come off as sulfur dioxide, a gas. Whenever a reaction gives a gas as a product, it favors the formation of a gas. We call that in chemistry increase in entropy. It's very favorable. So this will go, and as you can see from the mechanism, this sulfur dioxide comes off as a gas, and this chlorine here snaps back right in here to give that. So bottom line is, we can convert an OH, which is a poor leaving group, into a Cl, which is a good leaving group. Notice the retention of configuration, because the reaction is taking place at this oxygen and the chlorine is coming back from the same site it's leaving, that the sulfur dioxide is leaving. The importance of retention of configuration, you recall for SN2 reactions. That's highly stereospecific. So sometimes you need retention of configuration, sometimes you need inversion of configuration. But we'll have an example of that in a second. Let's look at another group that can convert a poor leaving group here, such as the OH, to a much better leaving group. This is called toluenesulfonyl chloride, or tosyl chloride, that's TSCl. As you know, we have a lot of acronyms for different chemicals in organic chemistry. So if you use TSCl, we'll understand it. So TSCl reacts with this alcohol. Let's see how that works. Here is the pair of electrons. This sulfur here, as you can imagine, is very positive. Why? Because it's bonded to electronegative oxygen, another electronegative oxygen, and an electronegative chlorine, which is also a good leaving group. So as you can imagine, this comes in and this leaves. So here's what we have as a product. This is called the OTS. So here's the oxygen from right here. And this group now is bonded right here. This is a very good leaving group. This entire group here is a good leaving group because it is toluenesulfonic acid, has a pKa that's pretty low. So therefore it's leaving its conjugate base, which is the OSOO, and the toluene group here is in fact a weak base. Let's see if we can apply that concept. So here is an OH. Notice the stereochemistry. It's pointing out, if you use tosyl chloride, you'll convert it to an O-tosyl group, maintaining the stereochemistry, retention of configuration. Here's an SN2 reaction. And we know it's SN2 because of the solvent here. And here is our nucleophile. If it's SN2, it goes by inversion. So you can see here, this product here has the CN inverted compared to the OTS. So this is out, and this is now in the back. So look out for that, because we'll do that quite a bit in synthesis whenever we need to make molecules with specific stereochemistry. So let's do a little summary here. So it's possible to take an alcohol and convert it to a good leaving group, Cl. So now you can see this can undergo your typical SN2 reaction much better to give a product, whereas this one it could not, because this is a poor leaving group. Same here. Primary halide. Notice this is tanyl chloride and this is oxalyl chloride. So you have a choice here in terms of reagent. So when you take your test or your quiz, you may want to have a little cheat sheet available with the different reagents ready, so you can know which one to use, or you have a choice in terms of which one to use. Here's another one, carboxylic acid. It's going to convert your OH into your Cl using tanyl chloride again. As we'll see in the last set of slides, the acid chlorides are very reactive compounds. How do we know that? Because the Cl is a good leaving group. So you can convert an carboxylic acid into an acid chloride and then take this on to other products. Let us look at the applications of these reactions now. So what we have done throughout this chapter is we've been studying acyl compounds with different leaving groups here. As we said, it's of synthetic help or usefulness if this leaving group here is a good leaving group, such as the chloride. If it's not a good leaving group, such as the alcohol or the acid or the amide, you'll have to make sure that you add a catalyst, such as H+, acid catalyzed, to convert it to a better leaving group. So let's look at the potential reaction here. Nucleophile reacting with an acyl compound with a leaving group that's good. We create a new molecule here with a new bond right here. Okay, typical example. Ethanol chloride. Reacting with propanol, we now make an ester with a new bond right here. So notice this is a much larger molecule than either of these two reactants. And the reason why it really works is because we have an acyl compound with a good leaving group and a nucleophile right here. So that's the concept that we need to apply to synthesis. So let's apply it to this molecule, this synthesis. So the question is, show how to carry out the following transformation. Let's look at this carefully, because the next two slides walk you through the analysis, observations, and the retrosynthesis. But let's just look at it. We start out here with chlorobenzene, which is a pretty common compound, readily available in the chemistry lab. So it's a good starting material. And we're making a molecule like this, an amide. And a much larger molecule. How do we do that? So we can see we have to bring in all of this. So let's do the analysis and see what type reactions and reagents are needed. Let's do the analysis. So here's the molecule again, the target molecule right here. You'll recognize this to be the amide bond right here. We can make an amide bond by an acyl substitution reaction using an amine. So if we had an amine right here, more than likely this is going to be the amine. And we need a group here that's a leaving group. So if we had this, an acid chloride, we can react this with the amine to get that. Now the question is, how do we get an acid chloride? You know how to get an acid chloride because you can react a carboxylic acid like this using tanyl chloride or oxalyl chloride to convert this OH here to a better leaving group. So the next question is, how do I make a carboxylic acid? You make a carboxylic acid by the reaction of a Grignard reagent with carbon dioxide followed by hydrolysis. And of course, how do you make a Grignard reagent? From a chloride, just with magnesium. So now that you have an idea of what needs to get done, the question now is, can you provide the reagents and the type reactions to accomplish this synthesis? So let's look at what's needed. To create the Grignard, of course, as we said, you need magnesium and ether as your solvent. To get the carboxylic acid, you react it with carbon dioxide. Remember, carbon dioxide is this, where this carbon here is positive. So the Grignard will react right here and, of course, kicking out those electrons to form the carboxylic acid after hydrolysis. Here's your carboxylic acid. This is a poor leaving group. It's best to convert it to a better leaving group, such as Cl. Tanyl chloride can do that job. Once you have an acid chloride here, you can react it with an amine to form this bond right here. So this is your target molecule by the reaction of an acid chloride, or the substitution reaction, acyl substitution reaction of an acid chloride with an amine to get the target molecule. And I think that's the end. And that's the end of chapter 16. So once again, I want you guys to really take your time and work through the problems in the book, work through the tutorial questions. We're getting to get a lot of chemistry involved here. So you have to really practice these questions and put these concepts together and apply them to solve problems. So that's the main key here, is to understand the concepts here and to utilize those concepts to solve problems. So once again, continue to study hard, and remember that as scientists, we are really problem solvers. We're really here to come up with creative solutions for problems based on the training and the tools that we have gotten here while learning organic chemistry. Okay, so continue to study hard, and I'll have more information for you later on in the week. Okay.